So in this video, we're going to talk about the laws of motion, or specifically Newton's laws of motion. So basically, we have three laws. First of which is, the first law, second law, and the third law. So right there, all right? Now, all the laws basically help you identify, talk about, and understand various kinds of motion. So let's start with the first law, the most basic law. Now this law is also called the law of inertia. So it's called the law of inertia. And inertia basically happens to be this tendency of a body to continue in a state of motion in which it started. So that means that if a body is at rest, it will continue to be at rest. And if in motion, it will continue to be in motion. So that is key. What I mean by these statements is the following. If you consider a box, say right here, if this is on a frictionless surface, all right, frictionless surfaces are usually drawn with these kind of sort of short lines popping out at an oblique angle. That is to ensure that this is frictionless or very, very smooth. All right. So if we have a very ideal case in which there is no friction, and this is a box of mass 10 kg, say, then what we would see that as time elapses, at t equal to 0, and say at t equal to 5 seconds, the box would still be at its position with the same mass and the same state of motion. Now, the same state of motion means that if it were at rest here, then it would still be at rest there. And if it were in motion, and in motion means basically, say it had some velocity. Say if it were moving with a velocity of 5 meters per second, it would continue to move with the same velocity, 5 meters per second. Now, in this case, we are conserving what we call velocity. And when we conserve velocity, we ensure that the initial velocity vector and the final velocity vector are the same. They're both at 5 meters per second in magnitude, and they both point in the same direction, which is this direction. So this is the law of inertia. Now this case only happens, and this is important, that it only happens when the net force acting on the body is 0. So that is to say that if, say, this box were in space, it would still do this. It's not being acted on by any force. That means it will continue to be in the state of motion in which it started. So that's the law of inertia, or the law in which everybody would try to maintain their state of motion, and hence, basically, is what inertia ensures, that tendency to continue to be in rest if it started at rest, or in motion if it started in motion. Now we can move on to the second law. The second law basically talks about situation where net force is not 0. So that is the case where we write this as follows: is not 0. Right. So net force is not 0 means that there is a force now acting on the box. Say this were the same box, 10 kgs. We have a force. So the force is being acted in this direction. Force of say 5 newtons. Newtons is just a unit in which we measure force. So if this is a force that's being acted on to this box right there in that direction, then Newton's second law states that the net force on the box would be equal to the mass of the box multiplied by the acceleration it develops due to that force. More fundamentally, this law is stated as the derivative of momentum of the body equals the force, or the net force. Now, it's very easy to see that because our usual normal understanding of momentum is because momentum is mass times velocity vector, therefore dp by dt would be d by dt of mv. Since m is a constant, because the 10 kg is a constant, in time it comes out, and you're just left with a derivative of velocity with time. A derivative of velocity with time is your well-known acceleration, and so this means that if this were the force, net force through this statement, then this implies the net force through this derivation, which is basically the statement right there. So with this information, this is something that Newton came up with empirically, more fundamentally. There are many ways to go about it, but this is the law that he came up with, and we can use this law in order to study what happens to the box. So we know the force is 5 newtons, so we know this part of the equation. We also know the mass of the box is 10 kilograms, so we also know this quantity right there. Therefore, we can figure out what the acceleration is going to be. So with that information, we have 5 newtons equals 10 kgs. Remember, this is newtons, and just a unit, this would be equal to acceleration, right? We're only considering magnitudes for now. That would mean that acceleration would be 0.5 meters per second square. So that's interesting, right? Now we know that this box is going to accelerate. It's going to accelerate constantly. With constant acceleration, meaning it will gain some velocity. It's going to get faster and faster and faster, and it's going to keep increasing its velocity at a constant pace. The constant pace is what we call acceleration. All right. So that is the motion. That's the case where net force wasn't zero. All right. And then the last case is rather simple. That's the case. That's the case of the third law. Now, this law is also known as the law of action and reaction. So basically, what the law states is that to every action, there is always an opposite and equal reaction. More formally, the law can be stated that for every force exerted by one object on the other object, there is an equal and opposite force exerted by the other object on the first object. So, to understand that, take the case of 2 boxes held close together like this. One is a small box, one is a large box. Now, what we are trying to do here is that if these 2 boxes are held close together, they are interacting. Then, say to the combined system, we push the entire system by some force. And that force, say, be 5 newtons. So this would ensure that the entire combination of boxes would move, right? And that would also be because this box would be acting another force on this box by virtue of this interface. And similarly, by action-reaction force, this box would also be exerting, big box would be exerting the same force in the same direction, in the reverse direction rather, on the smaller box. So that is the action-reaction force. The other way to understand this, one that comes more easily and logically, is to take the case of gravitation. Now, say we have the moon here and we have the earth here, right? Now, if that is the case, if the case of gravity is that they both will exert a force onto each other, now because of the gravity exerted by the gravitational force of the earth, which is exerted on the moon, there is a force like this, that is the force of gravity, so we call that F of g. Now, by virtue of this action force, this is the action force, the moon is also going to exert a force of a reaction force on the earth. So that will be like so. That will be minus of F of g, and I'm ensuring that there's a minus sign because the only thing I want to change is the direction. The magnitude will remain same, and this is what we call the reaction force. So there you have it. That's the action-reaction situation. Basically, any 2 objects which apply a force, which interact, basically apply equal and opposite forces onto each other. Now, this also goes with cases in which, say, you are standing and pushing a container. So we're trying to move this container. It's a rather heavy container, and what we are doing when we are pushing on it is we are ensuring that we're applying a force by our hands onto this box in this direction so that it can move in this direction. What we do not realize is that the box itself, by that virtue of action and reaction, is applying a force onto us in the opposite direction, but the same magnitude. So this is the reaction force, and this is the action force, and they're always equal and opposite. So Fa is always equal to minus F r, and that is if we take the vectors into account. So there you have it. Those were your 3 laws of motion. Newton came up with them, and they are very helpful in order to study dynamics. So I hope you like this video, and stay tuned for more.